Excellencies, Mr. Chairman, Mr. President, distinguished guests, faculty and students, good morning. My name is Kauthar Lutmani, and I'm honored to welcome you to the 6th edition of UM6P's Science Week. Every year, this week stands out as a cornerstone at the university. It's a moment where we pause to celebrate the power of inquiry. And this year, we continue to raise the bar under the theme of convergence, where we no longer look at science in isolation, but at the intersection where the future is actually being built. And with no further ado, to officially launch the discovery journey at the university this week, I'd like you all to help me welcome and join me welcome a leader whose visionary guidance continue to push the boundaries of what the university and the continent can achieve. Please, under your applause, Dr. Hisham El-Habti, President of UM6P.
Assalamu alaikum. Sabah khair, good morning. Okay. Ladies and gentlemen, dear colleagues, dear students, distinguished guests, it's really my pleasure to welcome you to the 2026 edition of UM6P Science Week. Over the past 5 editions, we have moved along a demanding trajectory. We have explored the frontiers of knowledge. We have grappled with complexity. We have navigated transitions. And last year, we dared to shape the future. Each of these themes was a step in a continuous movement to better understand the conditions under which knowledge is produced, transformed, and applied. At UM6P, we have chosen to place science at the center of that movement, a commitment to questioning, to structuring doubt, to approaching reality with both rigor and humility. This commitment takes a dual form: excellence in research and excellence in teaching. One without the other would be incomplete. Research without transmission remains silent. Teaching without inquiry becomes repetition. It is in their articulation that a university truly exists. Science Week emerged naturally from this articulation. It is the visible form of our mission. Each department, each laboratory of our community is invited to present not only its results, but its questions, its methods, its hesitations, its perspectives, because what defines science is the disciplined organization of uncertainty. From this perspective, this year's theme appears as a necessity. We are exploring a concept that is at once ancient and urgently new: convergence. For too long, the edifice of modern science has been built like a great library with separate wings for chemistry, for biology, for philosophy, for art. We have become masters of our own corridors, experts in our own rooms. This has given us depth, but it has also built walls. The great call of our time, the great challenge of our century, from the urgency of climate change to the enigma of consensus, refuses to stay within a single room. They stand in the hallways, demanding a new kind of inquiry. We see it already. Nanotechnologies speak to biology. Information sciences reshape cognition. Medicine becomes computational. Agriculture becomes systemic. What we call convergence is a structural transformation of knowledge itself. Yet, convergence is not only a matter of disciplines. It is also a matter of scales between the laboratory and society, between theory and applications, between discovery and industry. A university such as ours carries a specific responsibility in this regard. To ensure that knowledge does not remain enclosed, we hold the responsibility to accompany its transformation into technologies, into industries, into tangible contributions to Morocco, Africa, and the world. Ladies and gentlemen, in an age where our scientific and technological capabilities are expanding at an unprecedented pace, convergence amplifies both our power and our responsibility. It enables us to act across systems, to connect domains, and to address complexity. But it also heightens the consequences of our choices. The question is not only what we can do, but what we choose to do and under which frameworks of responsibility. This Science Week, beyond being a space for scientific exchange, is also a space for examination. In discussions on artificial intelligence and education, on migration and social systems, on tacit knowledge and African futures, it is not only about presenting knowledge, but testing its implications. We are creating the conditions for disciplines to confront one another, for perspectives to intersect, for disagreement to become productive. This brings me finally to an image. It comes from a text by the French philosopher and historian of science, Michel Serres, who wrote about the concept of the harlequin in the old Commedia dell'arte, wearing a coat of many colors, patches stitched together from different fabrics, different histories, different places. At first glance, it looks like a jumble, a disorder. But when you look closer, the coat holds together. It becomes a relation. Each patch touches another, and in that touching, something new is made. The coat has no single origin, no pure color, no original fabric. It is made entirely of encounters. This is what I wish for this Science Week, not only the convergence of disciplines, but of worldviews. I hope that we leave here not with our disciplines intact, folded and untroubled, but to leave here more like Harlequin's coat, marked by the encounters we have had, the patches we have received from others, the colors we did not know we could wear. And that, to me, is the real convergence. Thank you so much.
Thank you, Mr. President. And to truly understand the DNA of Science Week and the why behind our focus on convergence, we must look at the man who curates a scientific soul. He's a writer, an engineer, an economist, a man who personifies convergence himself. And so, please welcome our scientific director, Professor Fouad Laroui.
Good morning, everyone. That's not me, that's an avatar. Okay, why Science Week? Well, let's start by asking a very simple question. What's the difference between rationality and irrationality? What's the difference between being rational and being irrational? The difference is this: there is only one way of being rational. There is 1 million different ways of being irrational, right? Let's take an example. Rain. When it's raining, at the time of the old Greeks, there were like 1,000 different explanations, all irrational, about rain. Some were saying that the gods of the Olympus were crying, weeping. Some were saying that Zeus was actually urinating on us, sorry. There were a lot of, and then somebody, very clever guy, you know him, Socrates. He noticed one very simple fact. There is only rain when there are clouds in the sky. And he said, if there was the gods of the Olympus, it could rain without cloud. Then somebody else noticed that the clouds always come from the direction of the sea. And then, just by using rationality, now today, nobody disputes the scientific explanation of rain. Every irrational explanation of rain, and there were millions of them, have vanished, disappeared. And that's exactly how science has been proceeding for the last 2,000 years. Rationality has extended the domain of the explanation of natural facts. I'm not talking about metaphysics. Raphaël Liogier can talk for hours about metaphysics. I'm talking about natural phenomena. Now, the same colleague, yesterday I was having lunch with him, and he told me in French, I'll say it in French and I'll translate, Ah Fouad, ton insistance sur la science, tu es vraiment borné. Thank you, Raphaël. I'll translate. He said, your insistence on science makes you kind of a bigot, kind of a bigotry of science. No, that's not the point. What I try to convey, we try to convey to our students all the time, is that science is about what we can talk about. Logos, logos in Old Greek means talking, and means science, and means logic at the same time. What we can talk about, and that's what the great philosopher Ludwig Wittgenstein said, what we can talk about rationally, that's meaningful, that's science. However, that what we cannot talk about when we are praying, for instance, in the mosque, in the synagogue, in the temple, in the church, when we are listening to poetry, when we are listening to Kulthum or to Jean-Sébastien Bach, that's something we don't need words for that. But it's probably the most important thing that makes us human. So, yes, we have to be bigots of science when we are talking of natural phenomena, when we are writing equations to represent natural phenomena. But probably the most important thing is when we are alone with our faith, for instance. We don't have to talk. That's the last sentence of Wittgenstein's great book, Tractatus Philosophico-Logicus, said, what we cannot talk about, let's pass it away in silence. That doesn't mean that it's not important. It's probably the most important. But here, at this university, where, as Mr. President said, it's all about science, things that we can talk about in a mathematical way, write equations about. And that's what we want to do. And we want to be at the frontier of science. And that's why we have every year Science Week. Thank you.
Thank you, Professor Laruelle. Indeed, convergence is not just a technical process, it is a shift in our collective mindset. To expand on this philosophical and societal dimension, I'm honored to introduce Professor Raphaël Liogier.
Can I have these? Sorry. Can I have this? Yes? Yes. Of course, it's about convergence, but we also need to know why we have chosen this theme of convergence. Because, in fact, it's kind of strange to have chosen convergence, while what makes science successful is the exact opposite. For the entire 19th and 20th century, even starting in the 18th century, is divergence, is the fact that there was a process of specializations. Specialization in technologies, and specializations in different disciplines. So it's like if we are living a new stage, and it was just said, a new stage where there is a merging and integration of knowledge, that increase technological success. Now success is also due to convergence, well, because before success was due to mainly to specialization. So in a way we could, divide very succinctly, of course, broadly, the history of science in three main phases. The first phase is the age of confusion, we could call it that way. When I say confusion, it's not like a negative critique, because it was a very productive age in a way. The second age is the age of specialization, and now maybe we can call that the age of convergence. But first, before, I'd like to come back to why do we need science? Because it gives us something. It gives us a hint of those different phases, why we pass with those different phases. To do it very broadly and succinctly. First, there is this idea of neoteny, premature birth. That means premature birth, that makes human beings being some kind of incomplete being. Incomplete beings, so they feel this incompleteness, so the feeling of fragility. And so this feeling of fragility that goes with the sense of incompleteness makes human beings feel that they are a problem to themselves. In Greek, problem, that means obstacle. And you know that science, it's about problems. It's about trying to solve obstacles. And an obstacle is something that actually blocks the view. So human beings started to want to know what is beyond the obstacle, behind things. And it's what is called usually libidoscientia, the desire to know beyond phenomenon. Phenomenon meaning what appear. And in fact, what Fouad said about the beginning of science is the fact that you say something, you don't say anything, but even if it is a little thing that you say from where you say it. What was the path to say, that allow you to say something, even if it is a little thing? And the word path in Greek, it's methodos, it's methodology. What makes science being science is not to say big things, but to say from where you are saying it. So now let's talk just a little bit about the age, what we could call the age of confusion. It's confusion between faith and knowledge. The fact that on one side we have knowledge and on one side we have faith, but at that time, faith and knowledge was the same thing. Doesn't mean that it didn't accomplish things. It means that we couldn't distinguish between faith and knowledge, but there was the same aim, so to try to know what is behind some kind of a curtain. And there was also the confusion with what we could call magic and technology, because technology is about action, and magic is also about action. But magic is about action where you don't know where it comes from. For sometimes things works in magic, but you don't know where it comes from. So that's the reason why it's magic. And at one point or another, it becomes technology because you know where it comes from, why this action has actually been successful. And I'd like also to come to a point that is, I think, a quite interesting point because it's quite universal. The primary, the original science in all civilization is actually astrology, astronomy. Human beings, my PhD director always said that human beings are astrologos. It's interesting because it says something about human identity and about human science and at the same time human religion. Human beings are the only animal, seems like a detail, but it's not a detail, that are staring at the sky. So they are looking vertically, not only horizontally. Even birds, they look downstairs, right? But human beings, they take the chance even to be bitten, to be eaten by animals around, to do something and looking at the sky. And not only that they look at the sky, but they think maybe there is some kind of solution, interpretation about their destiny, about what they are and everything, and about the functioning of the universe beyond what is just right in front of them, being the earth itself. This says everything about human being and about this common desire to know what is behind the curtain, even taking the chance to be eaten, beaten immediately by what is in front of us. So it's because they do that, because they have this aspiration, what I call the desire to be in my work, that they started to build science. So now the age of specialization. The age of specialization started with classification. The fact that human beings started to see that there is one category, another category, another category. There are different types of animals. There are different types of objects. There are different types of relation between objects and animals. And so through that, they try to understand the relations between those categories. It has a name. It's the beginning of logics, the relation between those categories. And at that time, they started to separate two things. They separate religion and science, faith and science. They separate technology and magics, what is mysterious and what is not mysterious. But they also separate something, and it's less obvious. They separate techniques and science. And until the beginning of the 19th century, on one side you had techniques that was called art, mainly, not art as artistic, but art, the fact that you did something, and it was related to ancient recipe that you try to reproduce. If something will not work, you will say, oh, it's because I haven't imitated what my ancestor has actually transmitted me. So techniques was going this path. And on the other side, you had knowledge and science in itself, but that was very theoretical, without any application. Right? And the first time that we had a merge between science and technique, it is the beginning of technology. Sometimes people confuse technology and techniques. You know, the first time that we had technoscience or technology, it was with chemistry, actually, with Priestley in the UK and Lavoisier in France, where for the first time there was a theoretical thinking, and this theoretical thinking gave birth to something that could be applied. And one of the first things that could be applied, it was actually to light the street and to light the factory. And so it was one of the cause of the Industrial Revolution, because you could make people work right from 6 in the morning to sometimes 7, 8 in the evening, even if it was winter. And so it is the beginning of amplification of this process of acceleration that we know, because technology was at the service of science and science was the service of technique. But even in the 18th century, we didn't have that. If you read the Encyclopédie Diderot d'Alembert, you have an entrance for science, and you have a separate entrance for technique and separate entrance for art and things like that. Not many people know that it started technology and technoscience in the 19th century. Before it wasn't that, it was separated. So that's the first convergence. The second one, in the late 20th century, we had to wait until the late 20th, is inside technology, technique in itself, and science in itself. A process that I could call despecializations. Until the end of the 20th century, you had the different disciplines of science, physics, biology, but even inside biology, you have somebody that is working on molecular biology and somebody that is working on the behavior of animals, which is still biology, what we call ethology. They actually don't even understand each other. It's what is interesting, and it's what makes them successful. But in the end of the 20th century, we had this strange evolution where people were using biology to build mechanical things. For instance, in artificial intelligence, my friend Jan Leca, he has this idea to develop artificial intelligence by comparing, imitating neural networks. Neural, as they say, it's biology, but in the same time, it's also computing. And the other way around, you had some kind of engineer that has the idea to build prostheses that will be directly plugged to the body. So the body is biologic. If you plug it to the nervous system, it changes, even in medicine, the very definition of what is a body. Because the only medical definition of what is a body, a biological body, is actually the nervous perimeter. But if you plug a machine to the nervous system, you can ask, is it biological or is it not biological? And it is at that time that what is happening was what I call de-reconstructive technoscience. Because until this very time, the very end of the 20th century and the beginning of the 21st century, we improved the efficiency of what is already here. It's Descartes' idea that we improve the efficiency through science that was what is already here. We make more efficiency. But with the reconstructive technoscience, we actually change the very condition of, on one side, our own body. We have seen that with genetics also. We have seen that with, also prosthetics plugged on the nervous system, what I said. But also in nature. With what? With nuclear physics. Because when we talk about nuclear physics, and when we have this even idea of nuclear fusion, it means that one day we might be able to break the electrostatic repulsion, so to build elements, the elements that were built in the stars, with fusion in the stars, that we could fuse and create new elements. That means we will change the very soil, the very component of nature itself. So it's a difference of paradigm. It's like if we were taking charge of the evolution process itself. It reached to two new concepts, and I will finish with that. It reached two new concepts that actually gave me the idea of convergence for this theme. Is NBIC, convergence. That means, the idea that basically cognitive and information theory, bits of informations, and also nuclear, it could merge. And another interesting idea, a more recent idea, and more groundbreaking, but in the same times, kind of even more strange, is the idea of BANG. BANG is not an acronym like NBIC. It's an acrostiche. An acrostiche is when the meaning is the different letters and the word itself. Because BANG means B for bits of information, A for atoms, the structure, the very structure of the material world, N, for neurons, and G for genes. And the idea of people that are talking about bang convergence is like we are living a new Big Bang. So something that is singular, that has never happened in the history, not only of human beings, not only in the history of animals, of living beings, but in the history in itself, the history of the universe. And they said that they have this idea, there is an idea behind that everything is made of information. So at one moment or another, we will find the key to translate the information that are in the neurons, the information that are the genes, to the information that are into the structure of the material world. So this thing started with what we call information theory. There was at the Institute of Advanced Studies one of the founder of information theory, Gregory Scheitin, and we have an interesting discussion for 1 year about that. Is the world made of information or not? And so if we think the world is made of information, that just means that even the law of nature are like in a game, like a computer game where they are there because they were made there, but that could be other things because the rule of the game could change, and human beings dream of mastering the rule of the game. So this information theory reach what we could call an information ontology, saying like everything is made of information. And I will finish by saying that there is some kind of paradox saying that even if you have many scientists, like physicists, for instance, that deal with what they call digital physics and things like that, there is a very deep paradox. And I really finish by that. What means information data? What does that mean? Information, that means literally what gives a form to things, you know? It's an imprint. For instance, when you walk on the sand, there is the trace, there is the imprint of your foot on the sand. And what is left in the sand, the trace, the imprint, is the information. So what do mean those people when they say that the world is made of information? It's made of imprint, but imprint of what? Imprint of imprint of imprint of imprint. So my question is, where's the foot? I have some hypotheses about it, but because I want to please my very good friend Fouad Laoui, and he will say, oh, Raphael, again, you are too much of a philosopher, even worse, of a mystic. So I will not give my hypothesis. I will leave you with that. Maybe you'll have kind of an answer at the end of this week. Thank you very much.
Thank you, Professor Yuji. Thank you for taking us into the complexities of the human feature and the human nature leading to the age of convergence. Now, as we move into the heart of our keynote session, I would like to invite on stage a distinguished figure from our own community, someone deeply committed into advancing science here at UM6P. He will have the distinct honor of introducing a truly stellar guest whose work has reshaped the landscape of global health and medicine. Please join me in welcoming Professor Abdelali Haoudi.
Assalamu alaikum. Good morning. Distinguished guests, esteemed colleagues, ladies and gentlemen. It is both an honor and a great privilege to welcome you today to this special keynote session which also marks the inaugural and distinguished address of the CEO Forum organized by the Institute of Advanced Studies, or IES. Within the broader context of the Science Week of UM6P. Today, we are joined by an accomplished, exceptional global leader, whose career has shaped the frontiers of medicine, science policy, and innovation. It is my great privilege to introduce Dr. Victor Zhao, the president of the US National Academy of Medicine, one of the most prominent institutions in the world, who is guiding the health and science policy. Dr. Zhao is an internationally recognized global leader for his pioneering contribution to cardiovascular medicine, translational science, and global health leadership. Throughout his distinguished career, he has led some of the most prominent academic institutions, including Chancellor of Health Affairs at Duke University and President and CEO of Duke University Health System, as well as other prominent academic institutions, leadership positions in Stanford, Harvard, and other prominent institutions around the globe. Beyond his academic leadership, Dr. Zhao has played a critical role in shaping global health agendas, advising governments, international organizations, and institutions on pandemic preparedness, health systems transformations, and innovations ecosystems. His presence with us today is particularly meaningful. As the first distinguished speaker of the inaugural CEO Forum of the IES, his keynote sets the tone of what this platform aspires to become: a bridge between science, leadership, and strategic vision, connecting a global expertise with Africa's emerging innovation landscape. As part of the Science Week of UM6P, this moment reflects our shared ambition to position science and innovation at the heart of development, sovereignty, and global collaboration. Ladies and gentlemen, please join me in warmly welcoming Dr. Victor Zhao.
Salam alaikum and good morning. And thank you, my friend Abdullah Howdy, for exaggerated introduction. President Dr. Al-Habdi, thank you. And of course, Professor Fuad Lowry, and many distinguished guests and honorable faculty and students. First of all, I would tell you how greatly honored I am to give this keynote speech. You know, the Science Week is such a phenomenal concept. You're in the 6th Science Week and organizing this idea of bringing together scientists, faculty, students, and even the public to discuss science and to debate issues of science is so, so important. And of course, the concept is, and the leader of this area is Fuad Lowry, who's been very impressive in putting this together. Now, this theme, convergence, is timely and compelling. As you heard from Dr. Laugier, Professor Laugier, that in fact, we're now entering a different era from separate disciplines to bring disciplines together to solve problems. I'll talk a little bit more about this. I'm a physician scientist, a doctor, a scientist, and also a policy leader. So I look at this issue in a very practical fashion. And of course, Dr. Langier was extremely philosophical, if you will. And of course, what I'd like to do is to bring to you some real examples what convergence is. My focus, of course, is mainly in the area of health and medicine. So, I've been asked to speak on this topic, climate change, human health, and equity, the challenge, and how convergence science may help to attack and solve this problem. To begin with, as I said, when we look at health, it's not just medicine, it's not just healthcare. It's actually well beyond the issue, because we're recognizing that in health, we really are looking at many, many factors that influence people's health. And health is connected to change in our environment, in our community, in our culture, and of course, how we live and society writ large. So more than ever, we are so connected. I'm so glad I can be here today. It's only 7.5 hours flight. And of course, it was a wonderful opportunity to come to Morocco and to learn about all the exciting things that are being done here. And of course, UM6P, very exciting university. And of course, we think about this connectivity, an example of which, of course, is COVID-19, the pandemic, how so quickly one person or persons from one part of the world can quickly carry in fact, diseases to the other parts. But I think the larger impact that we think every day is social, behavioral, environmental determinants. And this is why we are beginning to think about medicine and health, that not just what drugs we take, how diagnosis, but how important it is to recognize the rest of the factors that greatly influence health. In fact, the data shows that only 10–15% of health outcomes are dependent on medicine and healthcare, much of which is genetic, social, environmental, and others. So let's think about this. The existential crisis of our time, there are many, but when I think about some three of those, they all involve humanity and human health. Of course, at the end of the day, this is what it's all about. What we care about is humanity and the good of our society. If you look at the global conflict that's happening just around here or every day elsewhere, the impact on human lives is unbelievable and, of course, unacceptable. And of course, many people are displaced from their home, they're refugees, and the health issue in these conditions are so terrible that as number one, I think global conflicts create tremendous inequities of health everywhere in the world. Second, of course, is pandemic. Another major disaster that we faced with, and thank God we got over COVID-19, but of course we should be very concerned about future outbreaks as well. And third is climate change. Climate change traditionally is thought to be an environmental issue. It's an issue of economy, but actually it's an issue of human lives. And climate change, to me, creates a health crisis that I'll discuss in the next few slides. So if you look at the impact of climate change, it's affecting human health because extreme temperatures, extreme weather, 5 million deaths per year. Air pollution alone causes also 5 million deaths annually. And of course, when you look at the change in climate, say it's global warming, mosquitoes are moving much farther up north and carrying more diseases. So vector-borne disease, 700,000 deaths each year. Now, what do we expect to see? Not only lives lost and suffering, but also a great economic effect. So if you look at the World Economic Forum prediction, by 2050, there'll be additional 14.5 billion deaths due to climate-related events. And of course, it impacts not only from extreme weather, but also chronic disease, such as cardiovascular disease, respiratory disease, many other reasons for increasing morbidity as well as mortality. The economic impact is huge because you look at the past 20 years, extreme weather cost $2.8 trillion globally. And in fact, in 2022 alone, 33 million people were displaced by floods, windstorms, earthquakes, and of course droughts. So that it's predicted by 2030, additional 135 million people could be pushed into poverty because of climate changes. So now you can see how important this issue is. It's important for humanity. It's important for our community. Now, I think it's important to recognize, as the talk I give about equity, that it disproportionately affects low-income countries. If you look at this slide I showed you, the richest 1% of countries are responsible for 2 times emission of the poorest 50% of countries altogether. So what's our responsibility as rich countries towards the rest of the world? Importantly, if you look at those dying from extreme weather disasters, low-income countries are 6 times more likely to be affected and 7 times more likely to die, people in low-income countries compared to high-income countries. So we, certainly the United States and countries which are rich, must have an obligation to look at how do we actually address this issue, because it's about humanity. In the post economy, you must remember that the population are very dependent on activities such as agriculture, forestry, fishery, and these are greatly affected by climate change and therefore impact their livelihood, and altogether creating poverty and many other problems. So altogether, I would say that climate change is not only an issue of environment, but I think is a major challenge to global equity and sustainable development. The UN SDG is going to be greatly affected by the impact of climate change. In Morocco, I looked into some of the information. It's quite astounding. For example, between 1971 and 2020, the temperature have increased in Morocco by approximately 0.43% centigrade per decade, each decade. The minimum night temperature rose by 0.39% centigrade per decade, with maximum daytime temperature at 0.52 degrees centigrade. I'm sure you all feel the effects of this increased temperature. But really what happens is it increases the risk of wildfires, damaged crops, strains of water supplies, irrigation demands, and drive up energy costs, consumption, and of course alter agricultural productivity. Also, it's predicted that in fact, by between 2040 and onwards, that rainfall in Morocco is predicted to increase by 14%. And that would accelerate the desertification, deserts, and of course increase sand and dust storms, and of course impact altogether on your society. Extreme weather events, severe storm, it will increase the risk of flooding and landslides. And finally, on your coastal region, it's expected that sea levels are going to increase by 0.21 meters by 2050, and as much as by 0.68 meters by 2100. So these are very severe issues that's affecting Morocco, and I'm sure that your government is well aware of this problem, but we need to address this now. So the question is how to address many of these issues. As you heard from previous speakers, no longer can we look at this in a more traditional way, because complex societal challenges cannot address solely by a single discipline or solely approach. Climate change implication spans sectors and disciplines. For example, energy sector, infrastructure, built environment, finance, behavior, so many others. So unless we all work together and act together in a convergent fashion, looking at competing priorities and incentives, by looking at ways to approach this, we're not going to be able to solve this problem. What is shown at the bottom of the slide is to say that traditional approach, as you heard from Professor Longier, that it doesn't work anymore. Now that's not to say disciplines are not good, because without disciplines and reduction, we would have not understood the mechanism in depth. But it's time to bring these disciplines together to look at ways to work on this rather than siloed effect. So what's convergence? Well, as been pointed out, convergent concept has been around for a while. But in 2014, the National Academy of Science, Engineering, Medicine, my organization, wrote a very important report to say it's time to bring these together. MIT also wrote a report about the future of health as convergence. What is really convergence? Well, we as researchers bring together friends and people with different disciplines to look at research. But convergence is deep integration of disciplines to solve a complex problem, focusing on the problem. Most of these are complex societal problems, such as climate change. So what this quote here says is an approach to problem solving that cuts across disciplinary boundaries, integrates knowledge, tools, and ways of thinking to form a comprehensive synthetic framework for tackling societal challenges that exist at the interface of multiple fields. I want to give you some examples in my field of where we're going in convergence before we talk about climate change. In the biomedical world, we see two major revolutions that happened in the 1950s to today. One is called the biomedical science revolution, and second is the digital revolution. And today, as you heard earlier, we now bring these together through AI and many others. So convergence is an example of the evolution of science to where we are today. For example, look at the slide. 1953, discovery of DNA by Watson and Crick, that opened up the whole area of understanding DNA and subsequently molecular biology. In 1972, DNA splicing and recombinant DNA technology was introduced. And of course, that opens a whole field, as I said, molecular biology, and of course, the creation of health sectors, of biotechnology sectors, such as 76, founding of Genentech and Biogen. But of course, we have used these tools forward in many good societal ways to create new drugs, new products. But in 1988, the National Academies first have reported to say we should sequence the human genome. This is before the technology was fully available. But as you know, sure enough, in 2001, the human genome was completed with a draft of a human genome itself, and that started the next revolution, the genomic revolution, where we're looking at what is the information we can get from genome, and of course, the discovery of CRISPR-Cas9 genome editing was opened up the door for using that information to really cure and treat diseases. That's genomic revolution. As I said, in 2009, we wrote a report, a new biology report, Academy, to say we have to start thinking what's in the future that led to the idea of what we call the convergent science in 2014. Now you can see how biologically we're moving in this direction, but look at digital evolution. From 1951, the first commercially available computer for simple arithmetic and data handling, to, of course, World Wide Web, the cloud computing, the whole idea of the first iPhone, and of course, the supercomputer, and now, of course, we have artificial intelligence. This same parallel revolution is now bringing us together to converge of using digital technology and biomedical evolution to ask the question health and medicine. And I'll give you 4 examples. Brain-computer interface, organized and 3D printing, AI-powered bioengineering, and of course, population health. In this one, I think you well know that if you look at brain-machine interface, they connect the brain and the nervous system to external devices. One can begin to transmit neural signals from brain to a device, enabling, therefore, the ability to create neuroprosthesis for people who have, in fact, as you can see in this video, impaired limb, but also for people with hemiplegia, paraplegia, and able to begin to utilize their brain to drive a machine, a computer, to do different functions. In 3D printing, when we first started 3D printing, we thought about creating medical devices, for example, implants, prostheses, but now we're bringing living tissues together. Next frontier is looking at functional tissues and organs, integrating cells, biomaterial, biomedical signals with 3D printing. Of course, in organ on a chip, we're using stem cell biology, microengineering, material science, and computation modeling to be able to bring together, organ on chip for testing without using animals now for drug testing, but also eventually you can imagine the use of all this generation of new tissues, etc. And of course, you all know about AlphaFold, the amazing power of AI in looking at 3D structures, protein structures, how biological molecules function, interact, and of course, how in fact you can look at biology, computation science, physics, and data science to transform how we model and design biologic systems. And let's not forget, equity and social science. This paper I wrote in Lancet to say population health is also convergent science. Because no longer can we simply say public health or medicine, we have to bring together social, behavioral, economic, data, legal, political science to improve the population health by creating the right policy, the right social environment to improve, in fact, health, and of course, creating equity. So these are some examples of what already convergent science can do in the biomedical area. As I said, my talk is more practical, and therefore I want to talk about climate change. Because for decades, climate change has been seen as one of an atmospheric and earth science system issue. But today we know it's reshaping so many parts of our society, and of course in human health and natural system, it's greatly shaping human health and natural systems altogether. And so today climate change is so important because solutions no longer rest with earth scientists alone, but it has to rest with many, many different sciences coming together, span disciplines and sectors, and durable solutions and priorities emerge at the interface of sciences, but also of governance, of markets and communities. Because many policies that we make around climate change is made beyond the health system alone, but by government and policy. So whatever we do as scientists, we should also think about how's our evidence helping policy making so that the right decisions are being made for humanity. So climate change demands convergence, integrating science, but also aligned policy. And of course, I'll talk a little bit about this, needing many sectors to work together. Now, why climate science and why climate and human health? These are some examples where climate is affecting human health and humanity. We already talked about extreme weather, agriculture by decreasing output, and poor nutrition quality, and of course, all the way to famine. Societal impacts, migration, economic strain, infectious disease, I talked about vector-borne disease and waterborne disease, and the concept of One Health, where you bring together environment and animal and human all together. If you think about the disruption we're having everywhere, deforestation, urbanization, right? It's bringing much closer animals and human beings approximately to each other. And of course, there are changes always in animal reservoir of diseases, and by this proximity of human-animal interaction and transmission, zoonosis, we now see the emergence of infection. More and more new infections, and of course, reemergence of previous infections, and consequently, the great increase in chance of pandemics. So, what would convergent science do? And I want to give you some examples of what's already happening in the area of climate change and health. Climate forecasting is an example. Second, looking at food systems. Third is looking at heat and health. Fourth is looking at circular economy by reducing emission, mitigation in healthcare. Another area is renewable fuels, and finally using AI to drive climate action and sustainable development. These are all work in progress, demonstrating that in fact in climate change and human health, there's a lot of work now by bringing together convergence. So first, let's look at forecasting. What you see on the right-hand side, the picture is, first of all, early days of climate forecasting, using mainly physics of atmosphere and ocean. And you can see over time, now expanded because of complexity to include Earth systems model today. That includes bio, geophysical, and chemical aspects of fully coupled system that involves atmosphere, ocean, land, sea, ice systems altogether. This robust modeling now, of course, is so much more capable by being able for us to forecast climate variability, long-term trends, what are prediction of acute events such as storms, heat waves, looking at rising CO2 and the correlation with temperature, the distribution of air pollution, the spread of waterborne diseases, and preventable death. So, as you can see, the capabilities now on convergence is enabling much better climate change and modeling. But now with the emergence of AI, it's really quite impressive machine learning strategies. Because using physics-based model, these will have to require high energy intensive supercomputers. Today, AI is coming in, not that it doesn't require a lot of energy, but much less in this case, that you can see in the bottom, physics-based model, AI-generated model, they almost look identical. But the AI model took 30 minutes to generate this information. So now you can see why bringing these technologies together in a real-life situation in climate change, of course, affecting human health, is going to be extremely important. Food systems. I talked very much about the problem of agriculture impact and food systems. And of course, the solution of now greatly impacting agriculture could well be a convergence approach. Because I think when you look at technological, biophysical, economic of the food systems, one can imagine now bringing many of these things. First, for example, climate-resistant crops, genetic engineering crops that can survive severe temperature, are drought-tolerant. And that, of course, will create a much better system to create sufficient food for many. Regenerative and smart agricultural practices, decision support tools to link climate forecasts to planting supply chain decisions, and of course, metrics to track health, environmental, and equity outcomes. So certainly that's another example of convergence. Let's talk about the impact of heat. As I mentioned, heat has been really a major source of death in poor countries. So, of course, in urban cities, where many of us live also, the climate, the heat effect on the elderly population, on the pregnant ladies, etc., is enormous, because the temperature in the urban setting is so much higher than, if you will, rise than in the rural settings. So really what it requires is look at what do we do about preventing the heat effect. It requires convergence in climate science, health technology, and the built environment. So climate modeling is important, but now there's in fact a lot of data and work done using biosensors that you can wear. People working in the fields, in agriculture and planting, migrant workers, which they can look at sensors to look at when the temperature is too high, the body temperature is too high, to say it's time, therefore, to stop working, and to monitor what's the extreme issue, warning systems. And of course, that also helps tremendously in policy making in terms of what is in fact the right condition for cities, for managing resilience, but also managing healthcare workers as well. In our field, in healthcare, believe it or not, in healthcare, actually is a major emitter of greenhouse gas. Globally, in healthcare, emits 4.5% of total greenhouse emission. It's huge because of the ventilation we need, because of electricity, because of the anesthesia gas, because of many waste that we have in disposable equipment, etc. So there's a really important effort to look at how to create a circular economy by looking at material science, engineering and social sciences, energy system to redesign the products practiced in healthcare. For example, a very frequent use anesthesia gas is desflurane, which actually is a great emitter of greenhouse gas. So increasingly, more and more in the United States, elsewhere, we're now stopping using this kind of anesthesia. Even, in fact, if you look at inhalants and many others, they create tremendous amount of greenhouse gas. But most importantly, we think about the practice during COVID-19 in your operating room, the amount of disposables, the waste is huge. So it's time to re-examine what is a much more efficient way. So that's another one of looking at recycled biomaterials, implants, modular repairable upgrade medical devices, and many others. And finally, look at renewable fuel sources. They are microorganisms which can live and resist extreme heat. So these extreme microorganisms can be engineered genetically so that they convert hydrogen, using hydrogen to convert CO2 into alcohol-based fuels, turning emissions into energy. So these heat-resistant organisms can remain active during fuel extraction and therefore improve efficiency and reduce costs. Here's another example of synthetic biology, chemical engineering, and energy systems and industrial process design to really create future renewable fuel sources which are much more efficient and cost much less, and of course, at the same time, being able to convert carbon dioxide into alcohol-based fuels. And finally, artificial intelligence. You already heard the phenomenal capability of AI in driving climate and health, predicting extreme weather, strengthening the grid resilience, cutting waste and resource use, reducing hospital energy use, expanding care with low carbon footprint, and improving diagnostic efficiency. So, ladies and gentlemen, I do strongly believe that convergent science, at least in this area and in many other areas, is going to be extremely important to address, to me, complex societal problems such as climate change, health and equity crisis, vulnerable populations, heat-responsive systems, mitigation air pollution, climate-resistant housing infrastructure, and I think implementing all this can accelerate the intervention and protect those at greatest risk. I want to end by thinking about the following. As we think about how is climate change, what are the drivers of climate change, recognize that it's not one sector, but multiple sectors. It's agriculture, it's transportation, it is construction, it's energy, it's health. So I think an important issue of addressing climate change is to bring all these sectors together, another convergence. Because these sectors work in parallel. If you look at the macroeconomic model of climate change, most discussion of each sector is how much energy consumption, how much carbon emission, and what's the economic impact. Rarely have we looked at it together, particularly on what it does to human health. So therefore, decisions made by each sector are done separately. And some may indeed improve health, but some decisions may actually make health worse. But if you look at the needs of a society, I would say human health, economic, and security are the three most important principles. By addressing human health, we'll not only create a more productive population, a healthier population, but also increase the economic as well. So what we're doing at the Academy is now creating a program, a major study, bringing together the agriculture, energy, heavy industry, transportation, and buildings, together the sectors, to look at what are decisions being made in greenhouse gas emission, and to look at what we call net zero emission to help the highest emitting sectors to improve health altogether. So our program is called A Pathway to Health for All Net Zero Emissions. And how do you do this? So in summary, I think climate change is a global crisis reshaping human economics and equity. And the impacts are interconnected, disproportionately affecting particularly vulnerable populations, indigenous populations, the poorer countries and poorer communities. Solutions, funding mechanisms, and governance structure remain separate, designed for more, as you said, disciplined approaches. So we now offer a major shift by bringing these things together. And of course, importantly, we have to think about all solutions have to be equity-centered. It's because it's all about our fellow citizens, our human being. Strengthen our local capacity and embed inclusive governance to think about the issue of policy. And of course, well, how do we do all this for the greater good? Thank you very much.
Thank you, Professor Zhao. You can stay on stage. A brilliant presentation that leaves us with much to reflect upon. To deepen this conversation and offer a perspective from the heights of scientific strategy, I now invite Professor Luis Fresco, President of the Strategic Advisory Board of the Institute of Advanced Studies, to join Professor Zhao. The floor is yours.
Assalamu alaikum, sabah al-khair, good morning, bonjour tout le monde. It's first of all a great honor, and I thank the organizers for inviting me to stand here. And thank you, Professor Zhao, for such a splendid, brilliant speech. Of course, there's nothing I could add. I could just say, guys, this is it. This is the final words. But of course, being a scientist, I know we always have to engage in discussion. So please take my comments as very, very tiny comments in the margin of this brilliant speech. First of all, as you know, certainly as Professor Zhao knows, the Chinese word for crisis consists of two characters. One is danger and the other is opportunity. And I think that's exactly what convergence is about. Yes, we are in a world which is called a world of polycrisis. Many crises are meeting and getting a form in a shape in our daily lives. Not just climate change, not just health, but for example, the current geopolitical situation is something unprecedented and will push us even further to find solutions. And so we have to deal with the crisis and at the same time seeing opportunities. And I think it's the role of universities to really help us, and especially to train young people to think in a convergent way. Convergence is not just a disciplinary bouillabaisse, a disciplinary potpourri of mixing disciplines together. It's really about thinking differently. And the big opportunity today that we have is that we have new tools at our disposal. First, of course, AI, artificial intelligence, which allows us not just to mine data and information everywhere, but also to recombine data and to explore frontiers and even to find things that we didn't know about. As some of you may know, the Nobel Prize for Chemistry last year was awarded to Deep Blue, which is an AI system in a way, but it did something really unusual. It explored molecules or proteins that we didn't know about, that we didn't know existed. So it's actually pushing the frontiers. And I think those are elements, those are tools in a way that can help us to deal with this crisis. On the crisis itself, or the convergence need, if I look at the health and the environment part, there is a matter of opportunity and a matter of danger. One of the dangers that I would allude to as well is that health means obviously not just human health, also not just animal health, domestic animals, although there is a real risk of interaction between animals and humans. All kinds of viruses could indeed move, such as, for example, bird flu, avian influenza, from animals to humans. But there is also, of course, what we call ecosystems health. And the World Health Organization has helped us to shape the concept of one global health, saying it's really the planet, the ecosystems of the planet, the species that are in there, the interaction with humans, and especially the way in which ecosystems are under pressure that will shape very much the reservoir of diseases of the future. This is about contagious diseases, but it's a really important part of the story. We know that Ecosystems under pressure have big changes in how species react and interact, and that is an additional source of problems. But of course, there's also an opportunity here, because we know that ecosystems and having green spaces in countries, but also at the level of cities, also help people, not just mentally, but also, for example, in capturing pollutants from traffic, for example. So green spaces, ecosystems, animals and humans are really tied together. And to my knowledge today, there is not one country that has an integrated policy on One Health in that sense of bringing everything together. So here's a chance for Morocco to be one of the first countries to do that. Opportunity, crisis, and danger. One of the dimensions of this whole story that I'd like to add to Professor Stau's speech is also the aspect of nutrition, human nutrition. We know, of course, that unfortunately there's still about 800 million people who are acutely malnourished. Most of those, if not all, are under conditions of severe civil unrest, stress, and war. And you know what countries and areas I'm talking about. But we have about 2 billion people who are actually malnourished because they don't get sufficient nutrients, vitamins, what have you, minerals. And that has very much to do with what they're eating, often not enough or too little variation. This is where there is a chance for us, not just to improve agriculture productivity, not just to improve the nutritional side, but also to think about balanced diets. Because the other part of the story, and this affects the global south as well as the global north, is that next to those 2 billion undernourished, poorly nourished people, we also have about the same amount of people who are either overweight or obese. And that is also a form of malnutrition. It's the body cannot cope with an unbalanced diet. And so actually what we need to do from a health perspective is to define what people will need in terms of the variety of foods, in terms of fibers, in terms of nutritional composition, and make sure that we take those healthy diets as part of the equation of how to solve the health, ecosystem, and climate change balance. Now, climate change, again, is a difficult concept because, yes, we know it has to do with higher temperatures, lower rainfall, and so on. There's one dimension that not everybody thinks about, and that is that higher temperatures also mean that some areas in the world actually can produce more than they do now. For particularly China, Canada, Russia, and Scandinavia, so the northern latitudes, actually the zone in which crops will be grown will slowly move up. For China, that means that maybe 100 kilometers from where now the boundary is of where you can grow rice, 100 kilometers more to the north, at the end of this century, they may grow more rice. So yes, there are some advantages, and even higher CO2 in itself is actually like a biofertilizer. It's actually something that may help crops. But of course, excessive CO2 that creates greenhouse gas emissions is something that we are very worried about. So again, it's opportunity versus danger. And it's looking at the opportunities of, for example, making better use of the land and of water that is so important. Probably the most important thing when it comes to land use, and mind you, 80% of the land that is available for agriculture, food production, and so on, is in the global south. The most challenging part there is what we call resource use efficiency, how to better use water, how to better use fertilizers, how to better make sure that we have a perfect connection between the soil, the crop we grow, and the way we deal with the crop. And there is so much to be done there. In my country, the Netherlands, we can now easily produce 10 tons per hectare of wheat on the best lands with the best techniques. This is not experimental, those are real farmers. In West Africa, for example, the cereal yields of millet or sorghum are still sometimes below 1 ton per hectare. I'm not saying that that can be a tenfold increase, but definitely there can be a huge increase. And then there is something that we should call disaster preparedness. Because yes, we have, certainly also because we know more about it, seemingly more disasters, environmental disasters than before. Yet the number of people that have died from environmental disasters in the last century has actually declined tenfold. About 500 million 500,000 per year in the 20s to 50,000 now. That is death. It's not disease or morbidity. But definitely we are learning to deal with things. However, we obviously have far more greater concentrations of people. In my country, we have looked at the issue of sea level rise, which actually affects a lot of countries in Asia as well. 1/3 of the economy of the Netherlands is actually below sea level. Half of the economy and 1/3 of the population. This is huge. So we were very worried when sea level rise would come. Will we actually have a country in a century's time? It turns out from all our calculations that it's quite possible to protect a country if you slowly invest in building higher dikes and in having areas where you can have additional floodwater stored for a while. And it's this kind of preparedness that we're actually now rolling also out in Vietnam and Bangladesh that helps you to think about how we solve these complex problems. It's the practicalities of converging engineering, economics, and also human behavior in a way that we can deal with crisis. The key issue is crisis preparedness. And the preparedness means not just only technological changes, but also very much policy and the mindset of people. And it's that is often lacking. Now, lastly, let me say a few words about convergence from a policy perspective. Because if there's one thing most countries are very bad at, including my own, it's about making sure that what we do in terms of regulation, whether it's for safety, health, genetics, for example, to have that coalesce into a concerted approach. There are very many barriers when it comes to changing rules for new technology, to changing ideas also at the policy level. Most politicians, and I'm not sure how many we have in this room, but most politicians know barely something about science. So there is an educational part there to be solved as well. Last but not least, this move towards convergence is obviously more than just combining disciplines. It's about thinking differently about the world. It's about taking responsibility. And that is so extremely important in a university. We are not just here in a university to train people in a certain discipline. We are actually also here for responsible citizens who will use the best of their knowledge and keep the openness of mind for the future when new science and new technologies will emerge. In 20 years' time, probably the AI that we have now will look obsolete. But we need to have the mindset to remain open-minded and to use the best possible science, the best possible knowledge and insight in a responsible way for a future society. Because only a society that is open enough to create new opportunities and to deal with the danger and the risk as well as the opportunity, that is a society that creates happy citizens and an equitable future. Thank you very much.
I can use both.
So we thought that in order for you not to listen only to monologues, we would get into a little discussion together. We did not prepare that. We are just calling each other Victor and Louise so that it has a little bit of a sort of homely atmosphere. And so, Victor, let me start by saying I've given you some comments on or some marginal comments on your talk. Is there anything that resonates with you?
Oh, your comments, everything. I think it's really, to me, a validation of this whole conference and about what I talk about using climate as an example, but you can easily see this going to food systems, as you said. I'd like to ask you some more questions on this, on any other issue, how today you just have to solve these complex problems by bringing in a lot more. As Professor Longier talked about, data system is so important. And of course, now we can imagine collecting the data, being able to integrate the information, standardize them, and then use algorithm to solve some of the problems.
Thank you. Perhaps let's turn a little bit to food and agriculture. Of course, I'm totally biased. As you know, it's my field. But we're also here sitting in a university with a very strong presence of OCP, which of course is all about fertilizer and hence about agriculture in the world. How do you see yourself from a health perspective, the future of food systems?
Oh, I was going to ask you that question because you started talking about this. I mean, I think you recognize a problem that we face between global north, global south, food distribution, as well as the kind of food that we eat in different cultures, etc., right? And I think about this as a huge problem. Of course, it requires both bring the science together to demonstrate what is in fact the best way to provide the best nutritious food that's affordable and accessible, but also policy issues. As you know, I mean, so much is dependent on policy because I think we are very much influenced by not only our culture, but the industry side of things, where there's so many different, shall we say, tasty foods that are being introduced with different, shall we say, processing. And of course, our country, we talk a lot about ultra-processed food. What do we need to do about this? What's the evidence? And how can you create some policy issues around them?
Yeah, thank you. That's also resonates very much with me. Unfortunately, when it comes to the science of food or nutrition, it's not that easy. This is a good example, I think, for all of you who think science is a clear-cut, easily solvable problem. We've had a couple of decades of epidemiological research on what is good nutrition, and it still is not so easy to say. There's not one miracle thing. It's not a matter of eating broccoli every day or an apple a day keeps the doctor away. There are a couple of things we need now, and we know that they work reasonably. They're not perfect. One is enough fibers. That's really a new insight, and that actually goes with what you're saying. So ultra-processed foods often mean that the fibers have been removed and there are a lot of chemicals added to the food. Fibers every day. The second is not too much fat and not too much sugar and not too much salt. Of course, eliminating sugar and fat in themselves would be a bad idea, not just from a food technology perspective, but also because we need some fats. Our body is also made up of fats. And we also need some sugar for our energy levels. But it's the measure of things. And indeed, as you very well say, in many processed foods that you buy in a supermarket, there is actually too much fat or too much sugar or too much salt. And one of the things that I always regret is that I think there's no country in the world which has nutrition and environment, for example, in combination, and agriculture as a subject matter in schools, which to me is quite amazing. We teach children high school or wherever about history and geography, and we don't teach them about the single most important thing in their lives every day, and that is what they eat and where it comes from and what it means to their bodies. So on good nutrition, to just finish that, there is no miracle food, but we know that diversity is very important. So you cannot say eating, for example, peanut butter by definition is always wrong. Things that are not off or not polluted can be eaten. But if you eat peanut butter sandwiches every day, you have a problem. But from time to time, even a few French fries will not kill you. What is necessary is diversity, fibers, and not too many additions. If you do that, you are a long way on the right road. But what is missing for many people most urban people, and as you know, we soon will have 2/3 of the world population in cities, what is missing is that most people have no idea where their food comes from. All of us, as we sit here, we are dependent on nameless, anonymous farmers all over the world who produce our foods. And there's very little gratitude towards that very important part of our economy. In fact, most young people don't want to be farmers. And if there's something, if you ask me, what keeps you awake at night, it's very often the question, where do we get the next generation of farmers? And it will not be farming in a traditional way. It will probably be very much high-tech farming, with all the advantages that we have of modern technology. But the gratitude towards those who produce our foods on the land and in the factories, I think is a very important thing not to forget in schools and universities.
Can I expand on a couple of things here? I think it's important to recognize there are tremendous cultural differences and therefore preference for food. So it's too easy for someone to come in to say, you must eat this or that, without having the data and evidence of saying, how do you actually make adjustment? So in the United States, we have a major program called Food is Medicine, whereby now there's hundreds of millions of dollars from American Heart Association, NIH, Rockefeller Foundation, to look at this fundamental issue. At least in our population, we need to understand, what in fact are the great, good nutritious food, but how does it fit into cultural context and provide evidence? Because in the long run, think about this, we have an insurance program that covers drugs and medicines and others, but in the UDGPH study that demonstrate that actually better food and lifestyle is better than drugs, the metformin, the insurance company doesn't pay for anything like this. So I think it's important not only think along this, the policy issue of getting the evidence, convincing policymakers that we must support, therefore, the proper nutrition for the right culture, the right society. Right. Second issue is information. I think if you look at the most frequently asked information in health, we work with Google and Microsoft. The most frequent question is nutrition. And the data for nutrition is terrible, the answers. And there's lots of really, say untrue statements. So we're now working on a way to say, how do you actually provide the right answers when someone searches for nutrition information? And this is where AI comes in. Because what we're working now with Google in a non-conflicted way is to look at curating all the published evidence-based data on nutrition. And enabling this, machine learning can begin to put together the right answers. We say 100 most frequently asked questions. Then the academy will use experts to look at the validation of the answer by machine, to do adjudication, machine learning, whereby at the end, the 100 answers are going to be validated through a combination of AI and experts. So those are the two really important ways to look at nutrition. To me, it's really a convergent issue, looking at science, data, approaches, policy, and information that enables people to make decisions. Final point. Medical schools are terrible in actually teaching nutrition.
Absolutely, I couldn't agree more.
And, so this has got to be another important area which we need to take this very seriously, but based on science and based on ability to communicate with the patients and the public, not simply to say, this is a food pyramid, you should eat more of this or that. I find those encounters with medical doctors and nutritionists very unsatisfying because they're not very useful most of the time.
Yeah, thank you. I couldn't agree more. Food is medicine indeed, but it's rarely applied that way. There is, of course, if I may add, a major social class issue. And we see in many parts of the world that the most poorly fed households are in fact households where the parents work too hard, or there's only one single parent who has no time to really cook sufficiently. So a story to tell is not you have to eat more green vegetables, because if you come home at 7 p.m. and you're really tired, you're not going to cut up the green vegetables anymore. So we need to have accessible food that is easy to be prepared and has all the nutritional qualities. And in my view, one of the things that's lacking in many countries is adequate school meals. And not just the meals served to the children, but also the way to prepare them. Even my students sometimes tell me that they cook, and I say, what have you cooked? And they say, yes, I put something into the microwave. Well, ladies and gentlemen, that's not cooking, as you very well know. So there's a lot to be done in this whole field of health and nutrition. But lastly, Victor, what are your thoughts for young students as they sit here or everywhere in the world? What can your life story bring in terms of thinking about the choices they have to make?
Well, first of all, I'm really excited to see so many young students here. Congratulations to UM6P. Congratulations Science Week. Fuad, I think this is an amazing concept because you get exposed to having people talk about science and get excited about science. But I get asked a lot of questions about careers. How do you make decisions about what do I need to do? How do I become Luis Fresco and many other leaders? I say to them, number one is, like what you do. Science is just amazing. Through science, you can understand so many issues. You can ask new questions. And by advancing science, I think you are doing really important issues. What I call the North Star. In fact, why do you want to do what you do? And why ultimately you want to do that? And that calls about purpose and impact. That's the number one. Because one cannot engineer your career or your research. You never know, as you said, opportunities come up and you follow what your passion is by looking at what's best for what you do, what you're excited about, and in fact, are you following your North Star? In our country, as you know, this past year, it's been very difficult and many cutback in science. So I ask a lot by young people what I do. I say, number one, these changes occur cyclically, right? Some years are better than others. You have to stay true to what you believe in. Second, you have to have good mentors, teachers who are able to help you think through this issue and be good role models. And third, of course, as I said, you always remember why you're doing what you're doing. And once you do that, I think opportunities will come. I never imagined what I'd be doing today. I was born in China. We're refugees from China to Hong Kong. I was an immigrant to study in Canada, United States. And today I say I'm doing what I'm doing because of opportunities that's offered to me. Such opportunity will offer to all of you if you do what's really best in your mind for the public.
Thank you. That's a very beautiful story. For the sake of time, I will not add other stories or my own story, but maybe one thing that I'd like to say to all the young students: be aware of what you're doing. Don't let time flow through your hands. Above all, keep a little diary, even a handwritten notebook or on your computer if you want, about your choices, not about it's raining today and so was not very nice to me, but no, what are the choices? What are the ideas that came to you? Who are the good teachers? Maybe put in some quotes in your little diary. And then from time to time, after a year, look at what you've learned, look at how you have evolved. I did that from when I was 16 years on, and I'm sometimes still amazed when I looked at my own diary. I already, of course, in a very primitive language, I thought I have to do agriculture, nutrition, and environment. And surprisingly, that's where I ended up, through a very roundabout way. So keep your diary. Above all, seek happiness and kindness, and learn from great teachers, such as Professor Zhao. Thank you very much.
Thank you so much, Professor Fresco. Thank you so much, Professor Zhao. That was a fascinating exchange, and those were words to live by and to carry for the rest of the week and for the rest of our path. So We've looked at policy, strategy, and science, but what about the visceral experience of convergence? Our final speaker of the morning session is a bioartist and a scientist who explores the boundaries of the self and the other. Please welcome to the stage, Professeur François-Joseph Lapointe.
Please don't leave the room. I have some exciting stuff to tell you about. Salam alaikum. Bon matin, good morning, sabah al-khir. Merci tout d'abord au professeur Laroui pour cette invitation. C'est la deuxième fois que je viens à l'UM6P en quelques mois. I was here last December for ISME Africa, which is a microbiology conference, and here I am again, this time for Science Week. It's my pleasure to give the second keynote, and as you'll see, it's about another type of convergence. The most beautiful of all, I should say, is the convergence between science and art. And today I want to teach you how to become an art scientist. As you may have realized by now, coming from Canada, a bilingual country, I could either give my talk in French or in English. Et bien que le français soit ma langue maternelle, I will speak in English today for the sake of clarity. Sometimes I may add a few sentences in French, ici et là. So here I am. This is all of my academic life summarized in just one slide. In 1992, I completed a PhD in biology at Université de Montréal. So on the left, that's me as a scientist. In 2012, I defended a second PhD. Yeah, I'm that kind of crazy guy. In the study and practice of art at Université du Québec à Montréal. So on the right, that's me as an artist. It took me 20 years to become an art scientist. And in the last decades, most of my research has been focused on bioart, which is the combination of art with biotechnology. So I guess that makes me a good candidate for advocating art-science convergence, and that's why I'm here today. My talk will be divided into 4 parts. First, I will give a brief overview of my practice as an art scientist. Secondly, I will present different ways in which art and science can work together. Part 3 is about the STEM to STEAM movement that I will explain later on, and that I will illustrate with numbers. In the last part, I will give you some recommendations to follow my footsteps and for becoming a hybrid individual who can do art and science at the same time. Part 1, an overview of my practice as an art scientist, with, of course, some bioart. I could talk forever about my own work, but I've selected 3 specific case studies to illustrate what I mean by bioart. Case study 1. This is my PhD work, my second PhD in the study and practice of arts. It's about choreogenetics, or how to dance your own DNA. Actually, it's not that difficult to dance your DNA. You just need DNA. And everybody has DNA. But you need to replace the 4 letters of the genetic alphabet by 4 distinct movements to create a choreography. Anybody can do this, but nobody could remember the very long sequence of A, T, C, and Gs that make up our DNA signature. In order to dance my DNA, I first had to sequence it. And that slide is presenting part of my DNA that was submitted to the Human Genome Project. As you can see from the first line highlighted in pink, it's a very long list of letters that I could not memorize. So to do so, I needed someone to read the letters aloud to me one by one so that I could execute the corresponding movement. This is a video showing the choreography. It's a dance piece for one person at a time, and this person is the one who is reading the letters to me. There's only 4 movements that I repeat over and over and over and over again. This is a solo piece that I executed for 3 hours. It's like running a marathon. This is the end of the video. I had to run out 3 times to throw up. I was exhausted. I'm supposed to run, but I can barely walk. That was 20 years ago. I was younger. After creating a solo piece that you just saw, I wanted to create a group choreography for more than one dancer at a time. But since every DNA sequence is different, I could not rely on someone from the public to read the letters. So instead, individual sequences were saved as audio files in MP3 format in such a way that each and every dancer could execute their own DNA sequence in a synchronized fashion. The partition for this choreography is presented as a file of aligned sequences. Each line is a different dancer, and the columns are the letters of their corresponding DNA sequences. 4 colors are used to distinguish A, T, C, and G. You can see by focusing on just 3 dancers that they share quite similar movement sequences. And yet, in some cases, we see genetic mutations in the DNA sequence of some individuals. This work reveals these mutations by comparing the sequences of a group of 30 individuals dancing together. This is a group piece that was presented in a shopping mall in Montreal. It's a 35-minute choreography only based on 4 movements. It was presented during a night of dance, repeating it 6 times from midnight to 6.
G, C, T, 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 T.
Sometimes you can see a mutation where all dancers are executing the same movement, and a single one is executing a different movement as your own DNA. The next case study is the famous, very famous 1,000 Handshakes project. It's an experiment to map the microbes between us. It implies to visit a new city, shake hands with as many people as possible, collect the bacteria in the palm of my right hand as I go along, and count the number of handshakes with a clicker. Then I go back to my lab, analyze the samples to create what I call microbiome selfies. I will now show you a quick video of a 3-hour-long performance that I did in Paris a few years ago. Je serre la main à tout le monde aujourd'hui. 650, 651, 652, vous pouvez être le numéro 653. Je serre la main à 1000 personnes aujourd'hui. 659, 660, 661. Partez pas sans me serrer la main. 730, 731, 732, 733. Bonjour. Je vous ai déjà serré la main. 851 et 852. Je dois serrer la main à 1000 personnes aujourd'hui. 973, 974. Bonjour, monsieur. Je serre la main à 1000 personnes. Vous êtes la 975e personne.
OK.
996, 997, 998, 999, 1,000. Voilà. You're the winner. This is you. All of you. Ouais, en 3 heures, 1000 poignées de main. C'est un bon score. Je suis satisfait. It was in 2014 that I presented this work for the first time at a medical museum in Copenhagen, where I shook 1,218 hands. Then in Montreal, in the middle of a cold winter in February, 1,000 handshakes. In San Francisco, for the Quantified Self exhibition, 1,001 handshakes. And from that point on, I started wearing a GoPro camera strapped onto my chest to capture people's reaction as I was shaking their hands. As you can see here at the National Experimental Art Forum in Perth, Australia, 1,001 handshakes. At the Berlin Transmediale in Germany, 1,001 handshakes. And in Baltimore, as part of the Culture as Medium exhibition, 1,001 handshakes once again, including a clown. In 2019, I was about to repeat this experiment in China. Of course, it was canceled because of COVID. So instead, I created another type of performance during the pandemic, the Zero Project Handshake. Total number of handshakes, 0. So when I collect microbiome samples, not during the pandemic, I have to go back to my lab, extract bacterial DNA, and sequence the bacterial communities to produce what I call microbiome selfies. And I'll show you what they look like. Here is one example representing a network of bacteria collected from the palm of my right hand after 150 handshakes, 300 handshakes, 500, 650, 850, 1,001 handshakes. All of these images are based on scientific data, yet they have also been exhibited in various museums and galleries around the world as art. Case study number 3, the Microbiome Rebirth Incubator. It's an artwork specifically designed to address the microbiome of newborn babies. It focuses on the transmission of bacteria from mothers to their babies during pregnancy and childbirth. So let's consider for a moment the transmission of microbiome at birth by comparing 2 babies delivered naturally or by cesarean section. Whereas the first one on the left will pick up the vaginal microbiome by going through the birth canal naturally, the second one on the right will not. Vaginal seeding aims at solving that problem by putting a sterile cloth inside of the vagina of the mother 1 hour prior to a C-section, and then using it to wipe the baby's face, mouth, and skin afterwards. This in order to inoculate or seed the baby with the vaginal microbiome naturally picked up at birth, but missing in babies delivered by C-section. When it comes to seeding, this medical procedure is currently accepted in cases of planned or elective C-section in various countries, such as Canada, the US, and France. I don't know about Morocco. Yet, it's not something you can do in cases of an emergency C-section when the life of the mother or the baby is at risk. And this is where my artwork comes into the picture. The Microbiome Rebirth Incubator is a large glass container filled with amniotic fluid into which vaginal bacteria in human breast milk are added to provide a source of good bacteria for the newborn. Here you see pictures of the seeding ritual of the incubator presented at Ars Electronica in Austria in 2018. It's a performance during which the incubator is filled with biological fluids. To do so, a breastfeeding mother, as you can see here, was recruited to nurse her baby and collect milk samples in the gallery space. While I was filling the incubator with breast milk, she went to a private room to collect a vaginal swab, which was then suspended in physiological serum and added to the fluids in the incubator. Recently, the incubator was presented in an art gallery alongside a video of the seeding ritual with 2 light boxes depicting the microbiome of a baby, either delivered by C-section, as you can see here on the left, or that of a natural birth, that you can see in the back here. Okay, part 2. Let's move now to something more general and not only focus on my work as an artist. I want to show how can art and science work together, or more precisely, how can artists and scientists work together, with a primer on paradisciplinarity that I will define later on. So according to some scholars, there exist 5 traditions of interactions between art and science. Art uses science, art is not science, and art presents a positive or a negative image of science. Art uses science, refers to the use of scientific techniques, materials, and principles of the making of art, such as anatomy, optics, engineering, or microbiology. These images on screen are all from actual artworks that use scientific methods or principles. Namely, I can point to the work entitled Away from the Flock by the famous artist Damien Hirst. It's the first image, top left. Ou encore, au centre, l'œuvre Méta-Harmonie de l'artiste suisse Jean Tinguely, qui s'inspire des principes physiques des engrenages. Art is science, or the scientification of art, is a tradition where scientific principles are used to interpret, to analyze, or to explicate art and aesthetics. For example, on the screen, one can look at the evolution of the Jackson Pollock dripping technique by computing the fractal dimensions of his painting from 1944 to 1954. At the right-hand side of the screen, randomization models can be used to generate false Mondrian paintings. Can you spot the real Mondrian among these images? Apparently, most people could not do it. Well, there you go. These are the 4 random Mondrian paintings. Art is not science, even when the subject is science. Refers to the work of artists who have been illustrating scientific metaphors in their work. Here you can easily recognize a painting by Salvador Dali in the middle, picturing a DNA molecule, or Frida Kahlo next to it, presenting a genealogy of her family. Art can present a positive image of science, like these beautiful roses with equations from nature in the background, or this other work representing the Tree of Life by Diego Rivera, a Mexican artist who also happens to be Frida Kahlo's husband. Finally, some pieces of art can present a negative image of science, or can be critical of the so-called scientific process. Namely, the Cult of the New Eve in the middle is a performance by the Critical Art Ensemble to illustrate how biotechnology uses religious metaphors to gain public trust. For the longest time, scholars have been describing art and science as 2 separate fields with different languages, different methods, and different objectives. The famous book entitled The Two Cultures by C.P. Snow exemplifies this separation between art and science. As a matter of fact, in the history of art-science interactions, 2 extreme positions have been proposed. For the proponents of separation, like C.P. Snow, art and science are 2 distinct fields of knowledge that cannot be compared nor combined. On the other hand, for the proponents of fusion, art and science can participate in the same quest for knowledge, in spite of their distinct methods and discourses. Roger Molina is the editor of the art science journal Leonardo. and he can be referred to distinguish among 6 different types of interactions between artists and scientists. Type 1, scientists who collaborate with artists on common projects, resulting in both scientific discoveries as well as the production of artworks. Type 2, scientists who apply their scientific research to understanding creative activities in the arts, where artistic activity is a research area in itself that illuminates the scientific domain. Type 3, scientists working with artists or humanities scholars to develop technological inventions. Type 4, scientists who engage in the arts and humanities to enhance cultural appropriation of science. Type 5, scientists who engage the arts and humanities to improve ways in which science is communicated to the public, that is, science communication. And finally, type 6, the most interesting one, scientists with dual careers, both as working scientists and exhibiting artists. Dual career is quite important in that definition. It points to individuals who contribute to the field of science with scientific publication and who also contribute to the field of art with artistic productions. Individuals like me, for instance. To prove my point, let me go back to the 3 case studies that I presented in the first part of my talk. Choreogenetics is a dance production. I've shown you the videos. But it is also a scientific paper published in the Proceedings of the Genetic and Evolutionary Computing Conference. The Microbiome Rebirth Incubator is an artwork that was exhibited at various galleries, but it is also a scientific paper on the transmission of the microbiome to the newborn, published in the British Journals of Obstetrics and Gynecology. Finally, the 1000 Handshakes resulted in performances in microbiome selfies, but it is also a scientific paper published in the French journal Images en Dermatologie. Besides scientific publications, what are the other possible contributions of artists to science? Well, they can assign different priorities to research objectives, ask different questions, help develop new methodological postulates, contest standard research procedures, bring new forms of knowledge, invent new technologies, interpret results in a different way, create new models for data visualization, and finally, help in the understanding of research results. Yet, dual individuals with trainings in the fields of art and sciences are extremely rare for several reasons. Robert Pirsig, the author of Zen and the Art of Motorcycle Maintenance, provides an answer, and I quote, "Today, we are overwhelmed by a mass of scientific data collected blindly. We are overwhelmed by a proliferation of new pseudo-artistic processes. We train artists without scientific knowledge and scholars who know nothing about art. In my opinion, the solution lies in education, in a pluralistic training of the arts and the sciences. Is this feasible? Is this desirable? For many years, various disciplines have sought to break free from their boundaries by opening up to other fields of research. Interdisciplinarity is when several disciplines collaborate towards a common goal. Transdisciplinarity refers to the crossing of boundaries to uncover new problems. But as for me, my personal experience shows me that this quest for inter or transdisciplinarity is not always fruitful or even effective. I preach for paradisciplinarity, a novel approach where art and science are evolving in parallel. And on a few rare occasions, eureka, hybridization, the grafting of 2 lineages. In the context of my hybrid practice of art and science, I've long used the term paradisciplinarity to define my stance. Here, the root para is not a reference to a byproduct of a discipline such as in parapsychology or parascience, but rather to a parallel practice of 2 disciplines, 2 fields of knowledge with their own methods, their own objectives, and their own languages. In this paper shown on this slide, I propose a definition of paradisciplinarity. which states that unlike interdisciplinary collaborations, which defines various interactions among a group of individuals working and coming together on a common project, for example, an artist working with a scientist, paradisciplinary applies to a single individual practicing two disciplines or more at once. To be truly paradisciplinarity, two axioms have to be satisfied. Axiom 1, parallelism. The fact that two disciplines must be performed by one individual in a synchronous fashion, that is, at the same time. The second one, symmetry, which implies that the importance of each disciplinary practice must be relatively equal in one's curriculum. That is, not being a scientist who also plays the piano as a hobby once a week. Using this definition, one can affirm that art science provides a specific type of paradisciplinary research and creation. An art scientist is an artist and a scientist at the same time. If this is true, art science is the bridge between two cultures, science and art. And the art scientist is the Swiss Army knife of research, a single tool that can do everything. Or rather, an individual who can understand the cultural differences of the interacting disciplines as well as the research itself. It doesn't mean that the collaborations are forbidden in paradisciplinary. Quite the contrary, but these collaborations often require an art scientist to facilitate the communication among artists and scientists working together, or to translate between languages. In fact, when we talk about art science, we often think that it's necessary to adopt a common vocabulary, to speak the same language. It's a fantasy. Just like Esperanto was trying to bridge the gap between cultures by creating a unique language for all humankind. It never worked. In this room, I would bet my life that everyone speaks at least two languages, and each of you can easily switch between English, French, Arabic, Dutch, Cantonese, Tagalog, or whatever. An art scientist is someone who knows the language of art, as well as the language of science, someone who knows how to translate from one language to the other. Finally, an art scientist is also a trendsetter, a groundbreaker, a pioneer. And I'm very proud of that slide. As scientists, we all know that the highlight of one's career is to publish a paper in Science or Nature, or in The Lancet, like Victor Zhao. I've never done it. Yet my photo was printed in Nature. Not for my artistic work, for my artistic work, not for my scientific research. And that was 13 years ago. Time flies. What is STEM to STEAM? The definition states that STEM to STEAM represents the evolution of educational approaches, integrating the arts, such as visual arts, music, or design, into traditional STEM subjects that are science, technology, engineering, and mathematics. I've made a quick search last week into STEAM programs at various universities worldwide on different continents, and this is getting very popular. Stanford, Boston, Toronto, Zurich, and Carnegie Mellon are doing it, just to name a few. UM6P, where are you? What are you waiting for? You could be the first university on the African continent to propose such a graduate program. Moi, je dis ça, je dis rien. Mais si vous cherchez une personne pour diriger cette initiative localement, je connais quelqu'un très compétent dans le domaine. So if you're not already convinced by the STEM to STEAM movement, I will try with numbers. A recent study published by University of Michigan revealed that the Nobel Prize winners are 3 times more likely to have an artistic hobby than the average scientist. More precisely, if you're into performing arts, you are 22 times more likely to get a Nobel Prize than the average scientist, 12 times more likely if you're into literature, 7 times more likely if you practice visual art, and 2 times more likely if you're a musician or a composer. I know that some of the students in this room are dancing, singing, or can play a musical instrument. I know of at least one student who also has a visual art practice. I've seen her work. Well, she is one step closer to a Nobel Prize than most of you who are only doing science. To convince you even more, I want to present the statistical analysis. I was trained as a biostatistician. I did a few years back an analysis for the SEED network, a network for sciences, engineering, arts, and design. After a call for papers on art-science interactions, some 40 contributions were received for a book on new forms of collaborations between scientists, engineers, artists, and designers. Based on these 40 papers, I did a textual content analysis listing the most common words used in the different papers. And I wanted to test whether the vocabulary was somewhat related to the status of the author or authors, being a scientist, an artist, or both. This is a clustering of all 40 papers using only word content. For the analysis, I was not interested in the name of the authors, but rather their respective disciplines, so the names were deleted. For the sake of clarity, I defined 4 clusters of papers by cutting the tree at a given level, and you can see now these 4 groups highlighted using different colors. These groups are clustered of papers that are using a somewhat similar vocabulary to discuss art-science collaboration. Then I computed the network analysis using the same data to identify more complex relationships among the papers. Here you can see the 40 nodes of the network colored based on the clusters they represent in the 4 colors. But more importantly, I wanted to assess whether the positions of these nodes in the network were related to the status of the author. Being only artists, the black nodes, only scientists, the white nodes, or hybrid individuals, the gray nodes. Network analysis and statistical tests using 3 different metrics revealed that hybrid nodes were the ones that stand out as being more central in the network. Such nodes, which with high degrees have higher numbers of connections with other nodes, a larger clustering coefficient, as well as a larger subgraph density. And this is all statistically significant. Using a subway network as a metaphor, where hubs are metro stations connecting 2 subway lines together, one can say the same thing about hybrids. They are hubs between artists and scientists, knowing both of their languages, using both vocabularies. Which takes me to the last and most important part of this talk. I will now give you my recommendations for becoming a hybrid just like me. But first, what is a hybrid? In biology, it is defined as a crossbreed among different species, such as the pizzly, the hybrid of a polar bear and a grizzly bear, a coy wolf, the hybrid of a wolf with a coyote, or a liger, the hybrid between a lion and a tiger. In the field of art science, we all know some hybrids. Namely, Leonardo da Vinci can be considered a hybrid between Galileo, the scientist, and Michelangelo, the famous artist. Although, historically, Leonardo was active and famous way before Galileo and Michelangelo, or rather before disciplines became separated. Just like the 2 cultures of CP Snow here again. So you want to be a hybrid? Let me give you some tips. Be patient. Don't be discouraged. Learn the technical tools. Study the distinct languages of art and science. Read the scientific literature. Attend conferences like this one. Visit art galleries. Go to museums. If you're an artist, talk to scientists with an open mind. If you're a scientist, talk to artists with an open heart. Experiment, experiment, and experiment. The secret is in the making. It's never too late. It took me 20 years. I'm going to end with a quote from the famous Charles Darwin. It's from his autobiography. And it summarizes in just a few sentences the importance of art for a scientist like him, so for scientists like you. For several years now, I've been unable to bear reading a single line of poetry. I recently tried reading Shakespeare and found him boring. Yes, I know. Boring and Shakespeare in the same sentence, impossible. Losing these tastes is not only a loss of pleasure, but it is perhaps also detrimental to the intellect, since it weakens our capacity to feel emotions. My mind seems to have become a machine for grinding together a large series of facts to derive general laws, but why this has caused the atrophy of the part of my brain that governs aesthetic sense, I cannot explain. So let me rephrase that to conclude. If you don't want your scientific brain to shrink, write poetry, play a musical instrument, dance, draw, paint, or do anything artistic that will bring you one step closer to a Nobel Prize. And with that, shukran.
Thank you so much, Professor Lapointe. The good side is that we are on time. The bad side is that we are not going to have time for the Q&A. So thank you so much for your enlightening insights. What an incredible morning has it been to kick off the 6th edition of the Science Week at UM6P in Bengurir. A huge thank you to all the speakers for challenging our perspectives. A huge thank you to you, our audience, for attending. And you are welcome to join us for the rest of the week. Before the break, I'd like to remind you that we have several sessions happening in the afternoon across the campus. Discovery. For lunch, you'll find several catering points across the campus. Please feel free to head there and enjoy your break. And with that, I wish you an excellent Science Week. Thank you so much for joining us.
Sitting all with me, but late. I'm gonna act with faith. Something you gon' see. I'm going back, baby. Something you gon' see. I'm never waking from this dream. I'm going back, baby, with me, but late. I'm gonna act with faith. It's something you gon' see. And I'm going back, baby. It's something you gon' see. But I'll never wake from this dream. hearts. Bring back some peace. Some peace of mind. Some peace of mind. Oceana.
It doesn't